Okay. All right, so to sort of summarize what we've sort of covered in the last couple of videos, we talked about just a few examples of the Laplace transform and the inverse transforms. And really all we're going to need today are, the following couple formulas, which you should have written down somewhere as sort of on hand and eventually memorize to sort of help solve the problems later on. Okay. So what we're going to use Laplace transforms in this class is to sort of solve IVPs. And these have a couple of advantages to sort of the normal way we've been going about solving IVPs. So one thing to sort of note is that it sort of lets you find the, in some sense, it lets you find the specific solution without finding the general solution. The other sort of advantage is that it really is, after we apply the Laplace transforms, most of the work is just straight algebra. So, solve via algebra. So those are like two positives, one maybe slightly con if these two are pros. Is, we're going to have to use a partial fraction decomposition. And, I know a lot of you probably don't like partial fraction decomposition, not your favorite topic in the world. And I will post a video in a bit. One of the next two will be on partial fraction decomposition. But I think that this is sort of as the kids say, sorry, not sorry situation. You're gonna have to learn partial fraction decomposition to get through this section. Okay, so the idea of how we're gonna go about solving an IVP with the Laplace transform is, let's say we look at let's say we're given y prime minus 8y equals e to the 2t. And we want to, and y of 0 equals 1. So the idea is we want to sort of take this and we just want to take the Laplace transform of both sides. So just sort of what we're going to then sort of do next is we'll get, something. We're going to use capital Y to denote, the Laplace transform of Y. We'll solve for Y. For y of s, capital Y. And then step 3 is just going to be like compute our original y in terms of the inverse transform of whatever we solved. Now to sort of go down this path, we sort of have a problem. So I mean, if we sort of look over here, we can split it up by the linearity property. And we know that the Laplace transform of e to the 2t is 1 over s minus 2. But now sort of our problem is, what do we do with this thing? Like, what does this equal? And so we're going to need to have a formula for the Laplace transform of a derivative. So let's go ahead and see if we can figure this out. So we want to compute Laplace transform of, say, the derivative of a function. Well, we can just plug it in directly. And ideally, we would like to end up with something involving the Laplace transform of the original function. So one thing we could do is do an integration by parts. We want to end up back with f of t instead of just f prime. And so we'll do integration by parts. Our u will be e to the negative st, and our dv will be f prime dt. So v is f of t, and du is negative s e to the negative st. So now we'll use our integration by parts, u times v, so f of t times e to the negative st. And then I always see a lot of people getting confused by this. How do you do integration by parts if you have bounds? You do the same thing. You pretend like you already sort of integrated this, so you're just going to plug in 0 and infinity. And then minus the integral from 0 to infinity of ft times negative s e to the negative st dt. We can pull out the minus s and we'll get plus s times the integral from 0 to infinity of f of t times e to the negative st. All right, and now you might recognize this integral. This is just the Laplace transform of f. So if I, again use the convention that I'm just going to denote this by capital F of s, just to make it a little bit easier to write, I get this. And now I can write this next part, f of t e to the negative st minus f of 0 e to the 0. And for this to even exist, for the Laplace transform of f to exist, I'm taking an infinite integral. So what this sort of tells me is that, well, the limit as t goes to infinity of this has to go to 0, because otherwise I'm, if it goes to like 1, well, I'm just sort of like I'm just integrating 1 from 0 to infinity, and that's going to diverge. So what we end up with is the following. That goes to 0. That stays as is, and we're left with s f of s minus f of 0. So to sort of sum up, if we take the Laplace transform of a derivative, we end up with s times the Laplace transform of the original function minus f of 0. All right, so in particular, a version of this, if I let the Laplace transform of y be capital Y of s, then the Laplace transform of y prime is s times y of s minus little y evaluated at 0. So now let's go back and solve that IVP. So we have solve y prime minus 8y equals e to the 2t, where y of 0 equals 1. And we're going to use the Laplace transform. Okay. So what we do first is just take the Laplace transform of both sides. Again, I'm just going to use this notation capital Y for the Laplace transform of y. But what I get is the following. So remember, I can split it up. Here, I'm just going to get negative 8 capital Y. And now I'm going to use this formula for y prime, s times capital Y minus y of 0, which is 1. And over here, I'm going to get 1 over s minus 2. So to simplify this a little bit, s y minus 1 minus 8y equals 1 over s minus 2. And now I can rewrite this as s minus 8 times y, add 1 to both sides, equals 1 over s minus 2 plus 1. I now divide by s minus 8. So y and I have a couple different options here. I can just go ahead and now I've solved for y of s, so now I need to compute the inverse transform. And to do that, I'm going to need to do a partial fraction decomposition. So you have a couple different options. You could combine these two fractions and do a partial fraction decomposition there. And that has an advantage of, I guess, just getting sort of a nice expression at the end, which you can then do that. Or you could just do a partial fraction decomposition for this part here. And I'm going to go ahead and do that. So 1 over actually, I'll do it off to the side. So 1 over s minus 2 and so I get the system a plus b equals 0 and negative a minus 2b equals 1. Well, negative 8a minus 2b equals 1. I can go ahead, say b equals negative a, negative 8a minus 2 negative a and so that's going to be plus 2, so I'll get negative 6a equals 1 and a equals negative 1/6 and b equals positive 1/6. So now I'll go plug this back in. I have a negative 1/6 times 1 over s minus 2 plus positive 1/6 1 over s minus 8 plus the additional 1 over s plus 8. So 1 plus 1/6 is going to be 7. Oops, I am skipping way too far ahead. And now I can just compute the inverse Laplace transform on both sides. So I know that right y equals the inverse transform of this capital Y. And looking at my table, this is something of the form s minus a. So I'm going to get negative 1/6 e to the 2t plus 7/6 e to the 8t. And that's going to be my final answer. So now, we did a partial fraction decomposition, but at the end, we just sort of got the answer, didn't actually have to find the general solution. Though you could also use this method to find the general solution anyway. Let's look at another example. All right. So right away, we're just going to compute the Laplace transform of both sides. So here we have s times capital Y minus y of 0 plus, again, capital Y equals Laplace transform of t is 1 over s squared. So using that y of 0 equals 2, we get s plus 1 times y minus 2 equals 1 over s squared. Move the 2 over to the other side. Oops. And so y equals, I'll actually go ahead and combine this. So this is going to be, right, s squared over s squared. And so y equals 2s squared plus 1 over s squared times s plus 1. All right, so now we're at the same point. We need to compute the inverse Laplace transform of this. And so we're going to want to do a partial fraction decomposition. So there's sort of two things to take into account. You want to make sure that at the end, every term that you have in the partial fraction decomposition is something that you can actually take the inverse transform of. Secondly, you got to make sure, that sort of everything we do, we can get something like this, in the form. So it's important to note that we can't just do a over s squared plus, I'm going to save some room, b over s plus 1. This is in no way guaranteed to work because you can sort of see what would happen if I tried. I would have a s plus 1 plus b s squared equals 2s squared plus 1. And so I would immediately run into an issue because if you look at the system, right, you would have, well, b equals, I guess, bs squared equals 2s squared. You would have, for the s term, you'd have as equals 0s, and for the constant term, you'd have a times 1 equals 1. So right here, this is a problem. This says a equals 0, this says a equals 1. So that is not going to work. Let's go ahead and erase that. So what we're actually going to need is another term for a lower power, and then still plus c over here. So now again, we'll multiply this to the other side. See what's going to happen, s squared, s plus 1. So the s squareds are going to cancel. We're going to be left with s plus 1. Here, b, one of the s's is going to cancel. And then finally, we're going to have plus c s squared. Okay, so I'm going to use an alternate approach than the one I have been using. And what we're going to do is sort of plug in different s values and solve for a, b, and c. So this has a couple of advantages and some disadvantages as well that I'll talk about later. So if s equals 0, I'm going to get 2 times 0 squared plus 1 equals a, 0 plus 1, plus b, 0 times 0 plus 1, plus c, 0 squared. And well, that vanishes, and I'm just left with a equals 1. So I've plugged something in, and I already have solved for one of the terms. Next, I could plug in s equals -1. And the reason I'm choosing -1 is because I can see that both of those things are going to go to 0 if I plug in -1. And so this becomes 3 on this side, a times 0, well, that vanishes. That also vanishes, and then plus c. So c equals 3. And then lastly, I guess I need to plug in one more term. Because I haven't solved for b yet, so I'll plug in s equals +1 just to plug something else in. No real reason for it other than it's kind of easy to do. And now I'll go ahead and use the fact that this is 1 times 2 plus b times 2 plus 3 times 1. And here I get 3 again. So I can cancel those. And this says b equals -2. All right, so a equals 1, c equals 3, b equals -2. I'll write this all out. So y equals, a was my coefficient for s squared, so s squared minus 2 over s for b, and then plus 3 over s plus 1 for c. Okay, so I have the inverse Laplace transform of 1 over s squared is just going to be t. That is going to be 2 times the inverse Laplace transform of 1 over s, which is just 1, and then plus 3 inverse Laplace transform of 1 over s plus 1 e to the -t. So this is my final answer. Y equals t minus 2 plus 3 e to the -t. All right, and just to end this video, try the following problem. Forgot to write down the IVP. Y prime minus 4y equals e to the 3t, where y of 0 equals 1. All right, so pause here, give that a shot. And let's go over the answers. So again, I'm just going to sort of give you the brief rundown. So after you sort of take the Laplace transform and actually hold on one second. So you should get something that looks like y, capital Y, is equal to s minus 10 over s minus 3 times s minus 4. If you do the partial fraction decomposition, you should get 2 over s minus 4 minus 1 over s minus 3, and then using that and the inverse transform, you would get y equals 2 e to the 4t minus e to the 3t. And we'll stop there.